Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 9 applied students who are looking for more help as they prepare for the Math EQAO in June. This is video number 8. In these videos we've been looking at applied EQAO questions from last year's EQAO, and they're available at this website here. And again, after watching the videos, if you have any questions or if you'd like to see more solutions on a particular topic, please post that in the comment section to the video. And let's get to the next question. So it's question number 28, and it's an open response question. So again, that means that it's being marked on levels out of 4, and you're expected to be a little bit more communicative and try to really fully address the question. So it says, Morrow takes a walk. The graph below shows the relationship between Morrow's distance from home and his walking time. So if we look at the graph, we can see that there's no values given. So we're not actually going to have specific numbers, but we can still talk in general about what's happening. So we have this first section, and then the second section, and then the third. It says in the table below, compare Morrow's distance from home, his speed, and the direction in which he is traveling in the various segments of his walk. Okay, so the very most important thing to look at when you're looking at a graph like this is this wording. This graph shows distance from home. That tells me that this point here is home. And that's important because direction, you can't make up a direction. So for example, you can't pretend someone's walking north. You can't pretend someone's going up a hill. You can't pretend that someone is going towards the CN Tower. The only thing we know is home is here. So this is walking away from home, and this is walking towards home. Okay, so that's how you have to discuss direction in one of these questions. In this case, the place we're talking about is home. In a previous graph, we had someone talking about Toronto, and we had someone who was driving towards Toronto. So in this case, this location, the bottom line represents home. So let's talk about the first chunk of the graph. Now, are they starting off at home? Oh, that's interesting. They don't even start at home. So they start, well, I guess let's use the person's name. He's called Morrow. And I think I'm actually going to type just because the writing with this particular tool can be kind of messy. And if I type, I'll be able to say a bit more and it'll be neater. So here we go, typing. So Morrow starts near home, but not at home, right? And we can see that because on the graph, if you look here, I wonder if you can see that. I assume you can see this. You can see that he is not quite at the bottom line, so he's not at home. So he starts near home, but not at home. He then walks further away from home. So he starts off away from home and walks further away. His speed was, now, can we answer this fully? Well, we don't have numbers, so I certainly can't tell you if he was going 10 kilometers per hour or 80 kilometers per hour. But this is a comparison question. So when I compare his speed here to his speed here, I can tell you when he's going faster. Faster is a steeper slope. And A is steeper than C. So even though I can't tell you exactly what speed he was going, I can tell you that his speed was faster than at any other time. So he starts near home, but not at home. He walks further away. His speed was faster than at any other time. Now, let's talk about part B. So again, I'm going to type because that way it'll be neat. Let's talk about the part B. Now, does he have any speed? Well, no, it's not at all a tilted line. It's a flat line, and that means that someone stays still, and the easiest thing to say is that they rest. So they're not going in any direction. But this is a comparison question. Can I compare anything? Well, I can compare somewhat the amount of time. So let's look carefully at time. So I'm going to do this. Oops. Get rid of those. Oh dear, now I'm really messing it up. Excuse me. I need to get rid of this. Delete. And this. Delete. So I'm just using this ruler function to get a really good idea about time. And the reason why I want you to pay attention to that is I don't know how long this is, but I know that this looks like twice as long. So if it took him 5 minutes to do part A, he's resting for 10 minutes. If it took him an hour to do part A, he's resting for 2 hours. So when you're comparing things, make sure you look at every part of it. So I'm going to say not only that Mario rests, but I'm going to say that he rests. Oops, type please. There we go. I'm going to say that Mario rests for about twice as long as the amount of time that he traveled in part A. So I don't know how long he rested, but I know it was twice as long as the time it took him to do part A. So now let's look at part C. Now, what direction is he going? We know that he's going home. Oh dear. We know he's going home. We've talked about that already. So let's type that. So in part C, Morrow walks home. Now, compare the speed. We already know that he walks slower here than in part A. We also know that it takes him, and look at the time that it takes to do part C compared to B or A. So it almost takes him double the time. It almost takes him the entire time to walk home as it did for him to walk there and rest. So what should I say? It takes him about as long to walk in part C as it took for parts A and B combined. So, did I do everything they wanted me to do? Did I compare? And remember, compare means always refer to other things. So, for example, I made sure that I said things like his speed is faster than at any other time. I'm comparing. When I said he traveled almost twice as long as in part A, I'm comparing. When I say it's slower than part A, I'm comparing. Make sure you compare. Did I mention speed? Yes. Did I mention direction? Yes. So I think that's a pretty decent answer. Let's go on. Okay, so back to multiple choice. These tend to go faster. Which dimensions would produce the smallest perimeter for a rectangle area of 120? So we know that if we are trying to optimize a rectangle, that we look for something as close to a square as we can get it. Now, none of these are necessarily a perfect square, so let's pretend that we forgot this information. I don't know. Which dimensions produce the smallest perimeter? So let's just calculate perimeter. So the first rectangle is 2 by 60. So 2, 60, 2, and 60. Add those up and you get a perimeter of 124. Let's look at the next rectangle, 3 and 40, 3 and 40. Add those up and you get 86. Next one, 4 and 30, 4 and 30, 4 and 30. Add those up and you get 68. The next one, 6 and 20, 6 and 20, 6 and 20. Add those up and you get 40, you get 52. So the other thing I need to make sure about before I go ahead and circle D is make sure that that's not a trick. Does this 6 by 20 rectangle have an area of 120? What's the area of this rectangle? Well, length times width is 6 times 20 is 120. So that is a valid answer. They will sometimes throw you ones that look like the right answer, but don't actually satisfy what they want you to do. So just don't fall into that trap. And again, if we think about it, these two numbers are closer to each other than any of the other pairs of numbers. So this shape is the closest to a square, at least of any of those numbers given. Okay, next question. Two square gardens, that's an important word. Two square gardens are shown below. A welcome banner extends from a corner of garden A to a corner of garden B. Which is closest to the length of the banner? So, in order to find the length of the banner, you can clearly see that it's the hypotenuse of a right-angled triangle. So that means I can label it as side C, label this as A and B, and write the Pythagorean theorem. But now I need to figure out, well, what is A and what is B? So let's look carefully at the diagram. A is one side of this square, and the square has an area of 42. So let's think closely about squares. A square is special because all sides are the same length. So if I call this side x, I have to call this side x. And therefore, what's the area? Area is length times width. Well, that's x times x. The area of a square is x squared. So therefore, 42 is x squared. So if I take the square root of 42, then I will know what the length of each side is. So if I square root 42 in my calculator, I get 6.5. So this side here is 6.5. Now exactly the same thing is true for this square. Again, this square here, all the side lengths are the same, so we can call them x or y or q, oh well, whatever. Therefore, 36, the area, is equal to x squared. So just take the square root of 36 and you'll know what x is. Square root of 36 is 6. So let's redraw a nice diagram here. This was 6.5, right angle. This was 6, and we were looking for the length of this side. So we need the Pythagorean theorem. Here it is. Let me just move down the page so we have some blank space. So c squared equals a squared plus b squared. And of course, I already know that 6.5 squared is 42 because, well, that's what I did right here. And 6 squared is 36. So c squared is equal to 78. Take the square root, and I can tell you that the length of the banner is about 8.8 meters in length. So let's go up to the multiple choice. Which is closest? Well, 8.8 is closest to 9. Okay, good Pythagorean theorem question. So I'm going to stop this video here because we're almost out of time, and I will meet you on video number 9.